Hello, welcome to the lecture number 27 of the course Quantum Mechanics and Molecular Spectroscopy. In the last class we were looking at the rotational Hamiltonian. Okay. The rotational Hamiltonian H rotation is given by L square by 2 mu R E square. No, I have used several, R E is identically equal to R naught is equal to R. So, that is nothing but the length of the AB bond, equilibrium length. Okay. So, that is R naught or R E. Okay. And this is rigid, that means it is not changing. Okay. So, the bond of AB is fixed length. Okay. That is also okay. So, this gives you what is known as rigid rotor approximation. Okay. Now, if that is the case, this can slightly be written as R square by L square by 2 IE, where IE is equal to mu R E square, and this is called moment of inertia. Okay. And the operator L square is the total angular momentum operator. Okay. Now, this value will be equal to L square operator, actually L square should be an operator. This will be equal to minus h bar square into 1 over sin theta d by d theta sin theta d by d theta plus 1 over sin square theta d square by d phi square, where theta and phi are angular coordinates as part of spherical polar coordinates. Okay. Now, there is also something called LZ operator, that will be equal to Z component of the angular momentum. Okay. Now, it turns out that the solutions of the angular momentum problem Okay, by the way, one can imagine this as particle on a surface of a sphere, or it can also be called as particle in a central force problem. Okay. Then what we have is the L square operator will have wave function yjm of theta and phi equals to h bar square j into j plus 1 yjm theta and phi, and Lz operator acting on yjm theta and phi will give you m h bar yjm theta and phi. Okay. Now using this one can write h rotation is equal to h rotation yjm theta and phi will be equal to, now h rotation had 1 over 2I as a additional this is, so if you go back, h rotation was equal to L square by 2IE. So we already know the wave functions of this L square operator. So only you multiply by this 2I, 1 over 2I. So that will be equal to h bar square by 2IE j into j plus 1 yjm theta and phi. So now you can look at your, so E rotation will now be depend on two quantum numbers j and m, okay, that is equal to h bar square by 2IE j into j plus 1. Even though the wave function depends on m and j, the energy depends only on j. Okay. So that is your E rotation. This E rotation is sometimes also written as E rotation Jm is equal to h bar square by 2IE j into j plus 1 or equal to h times Be j into j plus 1, where Be is given by h by 8 pi square IE, and this is called rotational constant. Okay. So now we know the wave functions and we know the energies. Now let us go back to the transition moment integral. The transition moment integral is given by f mu f mu dot epsilon I. Okay. Now, but your mu itself is written as mu naught plus d mu by dr, r is equal to 0 into r plus 1 over 2 t square mu by dr square evaluated r naught into r square plus etc whole thing epsilon to I. Okay. Now if you take rigid rotor TMI, if we have rigid rotor, then of course the R naught is a fixed value. Okay. Therefore, the derivatives with respect to R will not exist. Therefore, for rigid rotor TMI for rigid rotor will be equal to F, because this will go to 0 and this will also go to 0, all the other terms will go to 0. What you have is mu naught epsilon I, okay, where mu naught is called permanent dipole moment. Okay. Now your TMI is given by this. So you have to have mu naught. You have to have mu naught. So under rigid rotor approximation, for rigid rotor, okay, if TMI has to be non-zero, okay, TMI that is equal to F mu naught epsilon I, this has to be non-zero, then mu naught has to be non-zero. That is the initial, that is a minimum condition. If mu naught becomes 0, of course this entire integral becomes 0. So the mu naught must be not equal to 0. That means you can only have rotational transitions if mu naught is not equal to 0. That means the permanent dipole moment of molecules must be non-zero to record rotational spectra. Okay. So TMI equals to integral F mu naught dot epsilon. So for recording rotational spectra, the selection rule is the permanent dipole moment must not be 0. So only mu naught is not equal to 0, transitions will be allowed. Okay. So for example, if you have a AB diatomic molecule where A is not equal to B, then this molecule will have permanent dipole moment, mu naught is not equal to 0. But if you have a homodiatomics like AA, okay, then of course mu is equal to 0, mu naught is equal to 0. So which means you cannot recording of rotational spectra. Is not possible. Okay. So one of the selection rules for the recording rotational spectra is that the transition moment integral will go to 0 when mu naught becomes 0. So we can only record rotational spectra of molecules that have permanent dipole moment. Okay. Now let us look at the TMI little more carefully. TMI equals to F mu naught. And one thing that you must remember, that when I have this, that means if you take a molecule AB and your dipole moment is in this direction, let us suppose, okay. So this is delta plus and delta minus, then the dipole moment will be in that direction. So the propagation should be in this direction and the electric field should be, so your E, okay, should be along the dipole moment, okay, that is a selection rule. So this says that the electric field should oscillate along the because you are taking a dot product. Okay. Of course, you can come at an angle because you can always have a projection along that axis. However, if you have A and B and if your direction of propagation is like this and your electric field is like this and your dipole moment is like this. Okay. So, dipole moment is along, let us say, x axis, okay, and the propagation of light is along x axis, then your electric field will be along z axis, let us assume. So, this is my z axis, then of course x dot z will be equal to 0. Therefore, the transitions will not take place. Okay. So, it is not only that the mu naught must be 0, but the electric field must be aligned along the permanent dipole moment to have the transitions. That is this TMI. Okay. So, now once I assume that becomes non-zero, okay, that means the molecule has dipole moment. So, two things, one is molecule has permanent dipole moment and two, the electric field vector of the light has non-zero projection along the dipole moment. Okay. Only then the transition moment integral can become non-zero. So, TMI will be equal to F mu naught dot epsilon dot. So, I am only looking at this part. This part needs two conditions. One is the dipole moment must be non-zero, or the permanent dipole moment must be non-zero, and the electric field vector must be aligned or projected, have a projection along the dipole moment. Okay. Okay. If these two conditions are satisfied, then we can look at the following, the F and I. Okay. So, these are what are known as necessary conditions. So, these two are for recording the rotational spectrum. Okay. Necessary conditions, without these conditions of course one cannot record the rotational spectrum. Okay. Now, if you are what we have now, we have TMI is equal to F mu naught dot epsilon. So, we have already taken care of this. Now, let us look at the wave functions. Now, your wave function I will be equal to, now this will be the total wave function I. So, what will a total wave function I will consist of? That will consist of electronic part psi EL and the nuclear part, while I will call it as a chi nuclear. Okay. And similarly, there is a notation always, the ground state is given by double dash and the excited state is given by single dash. So, F is equal to psi electronic dot chi nuclear. Okay. Now the electronic is this comes from the electronic comment. So, what is electronic? H electronic psi electronic is E electronic psi electronic. So, this is the Hamiltonian that one needs to solve, and this H electronic wave function will H electronic Hamiltonian will consist of Ke of electrons, Pe of, okay, 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 electrons and nuclei and Pe of electrons repulsion, either this is attraction, and Pe of nuclei, this is repulsion. Okay. Now, so this is the H electronics, that you have to use different techniques, you have to do a quantum chemistry to solve that, but in this course we will assume that we know that. Okay. Now, the chi nuclear will have, so the chi nuclear will have two parts, one is the what is known as phi nuclear or phi internal into phi internal into the other thing is the translation. Okay. So, your I will now become psi electronic into phi internal into phi translation, and your F will be equal to psi electronic phi internal phi translation. Okay. So, now let us write the transition moment integral. So, your TMI will be equal to psi electronic phi translation and phi internal dash, okay, mu naught epsilon psi electronic phi trans and phi internal. Okay. Now, if you are looking at rigid rotor approximation, okay, let us think of a molecule AB separated by distance R0 or Re whatever, okay, some of, and then it is rotating. Okay. So, what will happen to electrons? Nothing will happen to the electronic part of the wave function remains unchanged. So, psi El remains unchanged. So, which means psi El double prime should be equal to psi El single prime, this is equal to psi El. Now, if it is rotating and it is translating, so the rotation will assume that rotation is not going to affect the translation. Rotational degrees of freedom and translational degrees of freedom can be separated out. So, then what happens is that phi trans prime will be equal to phi trans, this is called phi trans. Okay. And when you have the electronic degrees of freedom frozen, your dipole moment is not going to change. Okay. Similarly, when you have translation, if the AB molecule is translating, its dipole moment is not going to change. So, I can rewrite my TMI as psi electronic. Okay. So, this is now 3 integrals, isn't it? Psi electronic, phi trans, phi internal, mu naught epsilon, psi electronic, phi trans, phi internal. Okay, this is single prime and this is double prime. So, that is my. So, since the psi electronic and psi trans, these two quantities are not going to depend on this, then I can bring them out. That means I will have psi electronic phi trans and psi electronic phi trans, okay. Then what I will have is the phi internal mu naught epsilon phi internal double prime. Okay. Now, if your electronic wave function and translation wave function are normalized, then this will go to 0, or sorry, this will go to 1. Okay. Wave functions are normalized. Okay. Therefore, your TMI will become phi internal mu naught epsilon phi internal. Okay. So, for rotation, the TMI will now become, your phi internal is nothing but your rotational wave function. So, I will call it as a phi rotation in the excited state, okay, and mu naught epsilon phi rotation in the ground state wave functions. Now, we know this will be nothing but, if you take rigid rotor approximation, the phi rotation will nothing but y j m j prime m prime theta and phi mu naught epsilon y j double prime m double prime theta and phi. So, that is going to be your TMI. Okay. Your transition moment integral can now be written in terms of spherical spherical harmonics. So, transition moment integral can be written in terms of yjm theta and phi, which is nothing but your spherical. Okay. I am going to stop here and we will continue in the next lecture. Thank you.